Advanced linear motion. This presentation is really just a series of formulas, just extra formulas to add to your formula page. I'll go through it pretty quickly, and then we'll jump over to the other type of linear motion. So far we've talked about horizontal. We're also going to talk about vertical, also known as free fall. Anyway, instantaneous velocity under constant acceleration. That is, your object's being accelerated continuously, but the acceleration is not changing. Most common situation where this happens is in free fall, but that formula is that velocity instantaneous is equal to acceleration times time. Of course, because it's the velocity, the units are going to be in meters per second. As a side note, with abbreviations here, we use a lot of subscripts to denote things. Please don't let those subscripts confuse you. If they do, pick some other letter. Pick some other letter to be instantaneous velocity. Personally, I like to keep it the way most of physics does. There's lots of different velocities. We'll use I for instantaneous in this case. Here's another one. Unfortunately, I'm using v sub I again for something different, but the change in velocity with initial velocity. That is, we have an object, it starts out with a certain speed, then accelerates, whether that be speed up or slow down, and ends up at some final speed. This is our formula. Velocity final equals velocity initial plus acceleration times time. Again, because it's a velocity measured in meters per second. Another formula for you here, distance after constant acceleration, when we know both the initial and final velocities. Sometimes it depends on what's known and what's unknown. So under this particular circumstance, we have a constant acceleration, and we know our initial and final velocity. That is, we know how fast we were going to begin with, and we know how fast we ended. And then the total distance covered in that time is equal to 1/2 the velocity initial plus the velocity final. Really, all that is doing there is that is taking an average of those two velocities. We have an initial velocity, a final velocity. It was a constant acceleration, so all the velocities in between were nice and smooth. And so really all we're doing there is taking an average of the velocity, multiplying that by time, because a speed times a time will give us a distance. Because we're solving for distance there, by the way, the units, of course, are meters. Distance after constant acceleration, when initial velocities and the acceleration are known. So here we don't know the final velocity, but we know the acceleration instead. Then we can use this formula. As a side note, this formula also brings in an initial distance if the starting point is not at 0. But distance initial plus velocity initial times time plus 1/2 the acceleration times time squared. The last part of that formula will become very familiar to you. The rest of it, just copy down. These are all just plug and chug formulas. And the abbreviated version is there. And of course, again, being a distance, the units are meters. And lastly, the least common situation is when time is unknown. And we use this formula very rarely. Usually, it's the other stuff that's difficult to measure, the accelerations, the velocities, the distances. The time is usually one of the simplest. But when time is unknown, velocity final squared is equal to velocity initial squared plus 2 times the acceleration times the distance. One thing I'll point out here, I don't have units on here because you're not going to solve for velocity final squared. To actually get for velocity final, you have to take the square root of both sides to get there. If you're solving for one of the velocities, you would use, of course, end up with meters per second as your units, but it depends on what you're solving for, and that's true for any of these formulas. Pause the video if you need to copy these down, otherwise I'm moving on into distance and free fall. So now we have vertical linear motion. This is straight line motion up and down, also known as free fall. So free fall is when an object is falling only under the force of gravity. Now I should point out here, that never happens here on Earth. When an object is falling, you have air resistance, you might have some kinds of friction. Of course, air resistance is really just a picky case of friction. But this is physics. And the amazing thing, or the great thing about physics, is that we ignore the things that get in the way. So air resistance is annoying and makes the math really difficult. In fact, it kind of takes calculus to use, so we ignore it. We ignore air resistance. We ignore friction a lot of times. And so free fall is when an object is only falling under the force of gravity, no air resistance, no friction, and that's what we pretend happens. We'll talk conceptually about what happens if air resistance is a real thing, but we won't ever do calculations with it. And as a side note, the acceleration due to gravity on Earth is constant. The acceleration due to gravity is 9.81 meters per second squared, or abbreviated, we use little g for the acceleration due to gravity is equal to 9.81 meters per second squared. Keep in mind when you're solving a problem, if you don't know an acceleration and you feel like you have two unknowns in a problem, it might be that the object is falling and that your acceleration you always know. G is equal to 9.81 meters per second squared. We're also going to try to do a lab about this where we try to find this value. As a side note, the author of your physics textbook rounds this up to 10, and a lot of his math he uses 10, where you'll get nice neat answers if you use 10. If you use 10 on his problems, that's fine. In labs, which are real world settings, and test, I'm going to ask that you use 9.81 meters per second squared. Even though this is not a formula, please do put this constant onto your formula page. In my mind, this is kind of like pi is 3.14. However, I should point out, really, there's a second subscript that goes here. This is not just the acceleration due to gravity, but the acceleration due to gravity on Earth at the surface. Go to the moon, acceleration due to gravity is different. In fact, we'll do some calculations later on where we'll calculate the acceleration due to gravity other places. So then, once we have a flying object, one of the things we can use is the time it falls to calculate the distance that it fell. And that formula is distance in free fall, or d sub ff, is equal to 1/2 acceleration times time squared. Most common mistake on this is for people to forget the 1/2, or to forget the square, or worse, to forget both, or to forget that they know g, because g will not be given to you in a problem. You know it. It's 9.81 meters per second squared. And it's measured in meters because it's a distance. This last one here is really just a restatement of the v equals at formula, or v instantaneous is equal to acceleration times time formula that you had right at the beginning of this presentation here. This is just it applied to gravity. Notice the a becomes a g. Again, you could just use a as your abbreviation and substitute in the acceleration due to gravity, 9.81 meters per second squared. But that's free fall, and that's really all there is to linear motion. After this, we'll get into two-dimensional motion, which gets into projectile motion as well.